It's my absolute pleasure to introduce our guest speaker, Professor Sarah Hart. Sarah Hart is a mathematician and an author. She is a Fellow and Professor Emerita of Mathematics at Birkbeck College, University of London. She is also currently acting Provost of Gresham College, London, where she recently served a 4-year term as Professor of Geometry, the first woman to hold this chair since its creation in 1597. Sarah is particularly interested in cultural, historical and creative impact of mathematics and the links between mathematics and the arts. Her first book, Once Upon a Prime, explores the connections between mathematics and literature, and it's one of those connections that she'll be talking about today. The title of her talk is Life in Lilliput, the Mathematics of Fictional Realms. The talk will be roughly an hour long, and Sarah will take questions at the end. So Sarah will explore what mathematics can tell us about being very small or very large, both in fiction and in real life. So please join me in welcoming Sarah.
So thank you very much for coming. It's a Saturday morning and I know you had lots of other options for how to spend your Saturday, so let's make this as fun as I hope that you'll all see it is. Fiction, stories, films, books, they are all full of fantastical creatures, whether that's tiny people or tiny creatures, or at the other extreme, giants. So, for instance, just a few film posters. Many of these actually come from books. So on the left there, that's little Arietti Clock. So she's one of the borrowers from Mary Norton's fabulous books. I loved the borrowers when I was a kid, and I still love them. They're little people that live in your house, under your floorboards, or in little nooks and crannies. And if you are ever looking for anything, like you can never find a safety pin when you need one, right? You can never find a needle. It's probably been borrowed. And so these little people, you know, they are moving around and they are living their life, but what are their lives really like? Can mathematics tell us something about what life is like for, let's say, Matt Damon's character when, this is the film Downsizing, when to solve global warming, they decide that all humans should become 5 inches tall. Right, so you'll have to watch the film to see if that works out quite as planned. It's an idea. On the right here, of course, Gulliver's Travels, from the book by Jonathan Swift. In this case, Gulliver is played by Jack Black, and Gulliver visits actually lots of fabulous realms. The first one he goes to is Lilliput, where everybody is 1/12 of us, kind of scaled like a doll's house size. So that's the tiny Lilliputians who are taking him captive just there. But then later he goes to the land of Brobdingnag, where it's the other way round. It's full of giants that are 12 times us in all dimensions. So, yeah, what is life like for the tiny and the huge creatures of fiction? And yeah, there are some huge creatures as well. I like these 1950s B movies that are just kind of ridiculous. The Amazing Colossal Man, it says there, growing to a giant, to a monster. When will it stop? So when indeed, are there limits to how big people can grow, or creatures in general can grow? Or what about the terrifying ants that are due to something about radioactivity, they suddenly grow to vast sizes? And I have to say, in these films, unfortunately, I don't know why it is, when you're enormous, you seem to need to grab hold of a scantily clad young lady and put her in extreme peril. But there we are, I don't know, some side effect. And of course, King Kong on the right there, perhaps the most famous enormous movie monster. But he's essentially just a scaled up gorilla, right? So what is life like for the giants and the tiny creatures? Well, mathematics can really tell us a great deal. And in particular, there's one observation about what happens when you scale a shape up or down in size. It's very simple, but it tells us a lot. There are so many implications of it. It was first noticed by Galileo, who was thinking about when we're trying to build buildings, say we've got a dome. Domes are tricky things and they used to often fall down and not work out. If you've got a dome of a certain size in your building and the building has worked out, doesn't fall down, can I just double the size of that building? And will the dome still be structurally sound? I mean, obviously this matters as a question. And Galileo said, well, you can't just assume that, because not all of the things about shapes do in fact stay the same when you scale them. And so he propounded what we now call the square cube law, which encapsulates this. So imagine if you've got a shape, here I've just got a box, and we've doubled every dimension, right? So we've doubled the length, the width, and the height. So all of the lengths have increased by this scaling factor, in this case 2, but in general, let's say k, right? When you do that, all the lengths are increasing by this amount, scaling by this amount, but anything to do with areas, like the area of one of the faces, or the base, or the surface area, or the cross-sectional area, anything to do with areas, that's kind of two-dimensional quantity. You're, in effect, multiplying two lengths together, depending on which area you're calculating, you know, that will vary. But because you're multiplying two lengths together, you'll get kind of a double dose of that scaling factor. So the base, for instance, of the small box, just length times width. And then the double box, it's twice length times twice width, that's 4 times as much. So anything to do with areas with this shape, if you scale all the lengths by the same factor of k, the areas will be scaled by a factor of k squared, right? And then volumes, now we get the cube of the scaling factor. Because the volume of this bigger box, now you're multiplying 3 lengths together, twice length, twice width, twice height. So you get 8 times the original volume. So this box, just doubling it up, the area becomes 4 times as much when you get to the bigger box, and the volume is 8 times as much. And in general, when you scale by some factor of k, the area is increased by a factor of k squared, that's the square, and the volume is scaled by a factor of k cubed. So this is the square cube law. And I've kind of emphasized it because it's the single most important observation that we can make about what happens when you scale animals and people up or down, as we see in fiction. So let's think about the first implication of this rule, and that's if you're a giant. So here's a half giant. Actually, that's Hagrid from the Harry Potter book. So he's only a half giant. He's kind of twice us. He's twice as tall as us, twice as wide. So are there any implications for Hagrid, apart from, you know, he might need to eat a lot more? Well, I've got that formula there for pressure on the screen. And the reason is, let's think about if you are just walking around, you know, normal-sized human, why don't we just collapse in a heap? It's because our bones, our skeletons are holding us up. And so they have to be able to cope with, you know, reacting to the pressure that's caused by gravity wanting us to slump to the ground. They have to be able to hold us up, nevertheless. And so they have to be able to cope with pressure on those bones due to gravity, due to acceleration due to gravity. So we know the formula for pressure from school. Pressure is force per unit area. So we know that if you're putting the whole of your body weight on a very small area, then that's going to cause more damage than if we spread it out over a larger area, for example. That's why the area is on the bottom of this expression. So if you go to like a posh, stately home or something, you might see signs up saying, you know, no stiletto heels on this floor. That's because if you're wearing a stiletto, a very small heel, the whole of your body weight is concentrated over that very, very small area. That's going to cause damage potentially to a delicate floor. So that's why they don't allow it in these places. Okay, so pressure on your bones is the force that's acting divided by what area? Well, the cross-sectional area through your thigh bone or something. Okay, so we've got an area in that expression. We want to use the square cube law. What about this force? Okay, another maths formula. Force is mass times acceleration, right? Remember that one? So the acceleration in this case is gravity, right? Acceleration due to gravity. So force actually is determined by your mass. It's proportional to your mass. If your mass were to double, the force would double. So on the top there, we can replace force by, well, okay, mass. Mass depends on volume, right? Mass is proportional to volume. So the pressure on your bones is proportional to your volume divided by the cross-sectional area. Okay, so now I've got a volume on the top and an area on the bottom. Now let's think about if we scale, let's scale Sarah up by a factor of 10, okay? Like after I've eaten Christmas dinner. Scale it by a factor of 10. So now I'm like 55 feet tall, right? So what will happen to my volume? volume changes with the cube of the scaling factor. So my volume will have gone up by a factor of 1,000. Or in general, if I'm scaling by a factor of k, it'll be k cubed, right? The area, cross-sectional area through my now enormous femur will have increased by a factor not of 1,000, but 100, 10 squared. Area is increased with the square, the scaling factor. And in general, k squared, right? So if you're scaling by some factor k, the pressure on your bones is going to be proportional to, on the top, scaling factor cubed, k cubed, on the bottom, a k squared, volume over area. And there's some nice cancelling, and we just get this scaling factor k. So the pressure on 10 times Sarah will be 10 times greater than the pressure on my normal-sized bones. So how about Hagrid then? When Hagrid's walking around, he's twice us, so the pressure on his bones is twice what it is on our bones. So that's a bit more than usual, but you know, he's probably going to be okay. He probably shouldn't take up skipping, but he's going to be okay. However, those Brobdingnagians, now they are 12 times us. So the pressure on their bones is 12 times what it is on ours. Unfortunately for them, scientific studies of mammal bones have shown that although our bones can take a bit more than the usual amount of pressure, you know, so we can jump and run about and things without breaking our bones, there's a limit. And at about 10 times the normal amount of pressure, bones will break. So the Brobdingnagians are in serious trouble because they, just standing completely still, their bones are having to take 12 times the amount of pressure that, you know, human bones can cope with. And so they are not going to be able to even walk around. You know, their bones are all going to break as soon as they try and move. It's not a good lookout for giants. There is an upper limit to how big a giant can get. Or at least there is on planet Earth. But could we have space giants? You know, if you go out into the universe and in some, you know, work of fiction and you travel to a different planet where things are different, what about there? So we're unlikely to ever meet real giants on planet Earth, or at least not ones that are exactly like us, just scaled up, which is what you see in fiction. But what about out in space? Well, there is a story that talks about this. So it's perhaps not very well known, but Voltaire wrote a short, like a little novella called Micromega. It's kind of a satire. It's about human beings who are so pompous and squabble over little things and think they're so important, but of course their small arguments are really insignificant compared to, you know, the universe around us, right? So to show us this, he has a giant called Micromega who comes to visit planet Earth. He comes from somewhere near Sirius, and he is quite large. In fact, he's 24,000 times as big as us. He's 120,000 feet high. So, okay, when he gets to Earth, that's definitely not going to work. But could he, on his home planet, be okay? You know, so when he visits us, actually, he doesn't even see us to begin with. That's how insignificant we are. Then he realises we're there, and in a curious turn of events, he works out that he can hear us talking by making an ear trumpet out of his own fingernail clippings. So, you know, if you're going to ever interact with extraterrestrials, who knows what might happen. But Voltaire is a bit snarky about mathematicians. He says, well, these geometers are always very helpful, and they will find that since Monsieur Micromega, inhabitant of the country of Sirius, is 120,000 feet tall, that's 24,000 times us, and since we are hardly 5 feet tall, because people were shorter then, and our own sphere, our own world, 9,000 leagues around, it's absolutely necessary, he says, that the sphere that produced him, his planet, must be then this big number times greater in circumference than our little Earth. So what he's saying here is that, you know, mathematically, if he's going to be 24,000 times as tall as us, then his world must be 24,000 times as big, okay? So then that could work, he says. There's a problem with this. Here's the problem, that's not how gravity works. Suppose this is Earth, suppose you're out in space and you find an Earth-like planet, but maybe it's a different size than ours. How can you work out what gravity is on that planet? Well, luckily we have a law that tells us. So let's have some letters here. So this planet will have some radius, let's call it R. It'll have some mass, let's call it M. And for reasons we'll see, I'm also might want to call thing about is density. Okay, so here's an equation. We know that the force of gravity that you feel when you're standing on the surface of a planet, like Earth, will depend on, well, the universal gravitational constant that doesn't change, and then the mass of the planet, and then it's an inverse square, so we divide by the square of the radius, right? Okay, what's the mass of the planet? Well, if it's got a particular density, so density is mass over volume, right? So mass is volume times density, right? So if we take the density and multiply it by the volume, that's going to give us the mass. And if the volume is essentially related to the cube of the radius with a bit of 4/3 pi in there. But it's all right, because I'm just saying proportional to, so I don't care about the numbers. Okay, so we can plug that in. And if you see there, we've got a bit of cancelling we can do, and we find that the gravitational acceleration due to gravity at the surface of a planet with density d and radius r, that's how we obtain this gravity. In other words, if the radius doubles and the density stays the same, so an Earth planet but just bigger, if the radius doubles, gravity doubles. So if Micromega comes from an Earth-like planet with the same density as Earth, that's 24,000 times as wide as Earth. That will mean gravity is 24,000 times bigger. It's like way, way worse than it would be on Earth. He can't be 24,000 times the size. He'd have to be 1/24,000th of our size in order to experience the same forces. So that's obviously that's not going to work. Okay, well, all right. Well, maybe not all planets are the same density, right? Maybe there are planets out there that are so undense. I don't know what the word is. Whatever the opposite of dense is, have such small density that it'll be fine. Well, I had a look, and the lowest density of any planet that's ever been found is in planets that have got the nickname powder puff planets, right? They're very, very not dense. Their density is about 1% of Earth, but that's the lowest that's ever been found. Well, okay, even if Micromega lives on a planet like that, if it's 24,000 times the size of Earth, we're still going to struggle. Gravity will be 240 times as much. It's just not going to work. In fact, the only way a creature like Micromega could experience the same pressure on his bones as we do would be like if we lived on a planet that was the size of a grape. Right? So this doesn't work. There's no way to be 24,000 times as big as a human. You might get, there are, if you live on the moon, you can be a bit bigger, right? But these absolutely vast giants, even in space, it's going to be a challenge. All right, so life is tough for giants. What about the other extreme, though? What about journeying to Lilliput and seeing what the experience of being Lilliputian is like? Now, for them, the square cube law in terms of the pressure on bones is brilliant news, because their scaling factor is 1/12. So the pressure on their bones is 1/12 what it is on ours. That's fabulous, because it means they can lift many times their own weight. They're like super strong compared to us, proportionally. And actually it's this same observation that explains why, we see little ants carrying great big leaves that are far bigger than them. That's because of this square cube law. They are much stronger proportionally than we are, because, they're so much smaller. So yes, small creatures can carry many times their own weight. They are stronger in that sense. So that's the first plus. There's also some other things we can think about. Sometimes in stories or films which feature tiny creatures, shrink ray victims or borrowers or anything like this, you get perilous situations of jeopardy where, for example, the bad guy catches this tiny person and puts them on top of a high shelf, and then they look down and it's, oh my goodness, it's 30 centimeters to the floor, it's a terrifying drop, and we're all doomed. So let's think about that a little bit. That. When we fall, there's two forces really that are acting, roughly speaking. So gravity, of course, but then, if you go skydiving, gravity is acting downwards, but air resistance is acting upwards. Gravity depends on your mass. And air resistance, so air resistance initially, nothing, you're not moving, but as you pick up speed, the air resistance will increase. And in fact, it's roughly speaking proportional to the square of your velocity. And it also is proportional to the area, kind of in contact with the air. Now, as you speed up then, the air resistance that's pushing upwards will increase because of that v squared. Gravity is going to stay the same. So gravity is pulling you down the same amount, air resistance is increasing, and at some point, those forces exactly balance out. If you're going fast enough, the forces balance out, so there's no net force, so there's no net acceleration, so you don't speed up anymore. And that's what terminal velocity is, right? That's when you just you continue at the same speed. Now that speed can be quite fast, so that's why parachutes are so useful, because parachutes increase your surface area hugely. So that means that this equilibrium is reached at a much lower velocity. And so the terminal velocity when you're using a parachute is much, much lower. So that's why we use them. So if we think about at this terminal velocity, these two forces are balanced. So you'll have a relationship between the mass, there'll be some constants in here and here, but there'll be a balance between the mass on one side and velocity squared and area on the other side. So if we want to find terminal velocity, we're thinking about the Lilliputians then when we scale up or down, we just rearrange this a bit, we find that at the terminal velocity, this terminal velocity is proportional to, well, it's mass over area, and then you have to take the square root. And we've got a mass and we've got an area, right? So mass depends on volume. Volume is proportional to the cube of the scaling factor, and area to the square of the scaling factor. So if we're now thinking about a Lilliputian, we can work out a Lilliputian's terminal velocity if we know the human terminal velocity. So that's what we're interested in here. So with a scaling factor of k, on the top of this equation you'll get k cubed, because it's to do with volume, and on the bottom k squared, bit of cancelling, boom. So now let's work out the Lilliputian terminal velocity. Okay, so their terminal velocity will be proportional to the square root of the scaling factor. Okay. So what's human terminal velocity? It's about 50 meters per second. That's too fast. Don't ever reach that. Take your parachute with you. That's not good news. What about the Lilliputian terminal velocity? So we have to take this number and multiply it by the square root of the scaling factor, the square root of 1/12. If we do that, we get 14 and a bit. So that's lower than the human one. Okay, good. But it still feels like if you're tiny, that might be, well, it might be terminal. So that looks a bit worrying. But here's what we have to remember. Falling isn't the problem. The problem is landing. So what happens when we land? Here's a terrified shrink ray victim just there. Oh no, she's going to climb onto the top of this chair, but then will she fall off? Will it be a disaster? That's from a film called Dr. Cyclops. He's mad scientist, 1950s, I guess. So it's landing that's the problem. When you land, you've picked up a lot of energy. You've got kinetic energy from moving. And suddenly you come to a stop. All of that energy has to go somewhere. It's dissipated over the impact area. So at a point where, when you land, what your kinetic energy is going to be will depend on your mass and your velocity, half mv squared. That's the formula for kinetic energy. And then that's got to be dissipated over your impact area. And there's a kind of speed beyond which, it's not a good idea to be going when you hit the ground. And NASA has done some tests, not, I hope, with real humans. They've done some tests and they found that actually up to an impact speed of about 12 meters per second, basically fine, should be more or less unscathed, might twist your ankle, but nothing serious. Above that, then the risk of serious injury or worse gets very high, much higher. So let's say 12 meters per second then is kind of, we're okay. So how do we work out what the equivalent number is for Lilliputians? So at that maximum survivable velocity, let's call it, again, you'll have a relationship between kinetic energy on one side, mass and velocity squared, and area on the other side. So that actually inverts the equation we just saw, because when we were thinking about falling, we had mass on one side and velocity squared and area on the other side. So I won't go through all the details, but you can if you like. The implication is that at the maximum survivable impact velocity, that will change when you scale the creature involved with not the square root of the scaling factor, but 1 over that. So let's work out this for Lilliputians. For humans, 12 meters per second, that's the key number. So to find the equivalent number for Lilliputians, we have to multiply by the square root of 1 over the scaling factor. So 1 over 1/12, that's a 12. That's 12. So that's the answer for humans. For Lilliputians, it's high, it's 42 meters per second. They can survive an impact at 42 meters per second. So you might notice something here. The terminal velocity for Lilliputian is 14, and they can survive up to 42 meters per second. What this means is a Lilliputian can survive a fall from any height. You could throw a Lilliputian out of an aeroplane, it wouldn't be very nice, but you could, and they'd be completely fine. You can chuck a mouse off the Empire State Building, again, don't, but they'll be fine at the bottom. Small creatures do not need to worry about falling from height. They are going to be completely fine. So this is bad news if, for example, you've ever thrown a spider out of your bathroom window, because when it gets to the ground, it's going to be absolutely fine, but now it'll be angry. So just, as a warning. So Lilliputians, they're strong, they can survive a fall from any height. Also, they can jump really high. So something we sometimes hear in the media is that, fleas are the highest jumpers in the Animal Olympics. Fleas are going to win the high jump because if a flea was the size of a human, they'd be able to jump over a house, right? No, they wouldn't. They wouldn't. Fleas can jump, about 6 inches, and that's good. But actually, when you do these calculations about what happens when you scale things, your ability to jump is determined by muscles, and the distance you can jump is dependent on the volume of muscle. And so when you scale up, the volume of muscle will scale up at the same rate as the volume of the rest of you. So in fact, everything sort of cancels out, and what it means is that a giant-sized flea can jump exactly to the same height as a normal-sized flea. So they can't jump over a house. They can still just jump like 6 inches. But what this means for Lilliputians is a Lilliputian can jump to the same height as a human. It's about like 1 meter. And so that's great, right? So you can't trap a Lilliputian by putting it in a bucket or something and going, ha ha ha. They can just jump out and run away. So again, good news for the shrink ray victims in all of this. This is great. Now there are a couple of downsides to being tiny. And one of them is kind of specific to the inhabitants of Lilliput. And it comes from, so Jonathan Swift, he gives what I like to call performative arithmetic. He makes this travelogue of Gulliver have this kind of air of scientific, credibility by giving lots of numbers and details. And this is great for us because he tells this is exactly what we've got to go on. He tells the exact sizes, and all throughout his book there are lots of things going on. He has a few digs at mathematicians. I think there might be some Swift experts in the audience, didn't absolutely love Isaac Newton. A lot of people, sorry, we're at the Newton Institute. Newton was obviously marvellous, but he perhaps didn't approve of some of the things Newton was doing, I think, when he was master of the mint. But anyway, so he did think mathematicians could perhaps be not necessarily entirely practical in their thinking. So later on, Gulliver actually goes to the island in the sky, Laputa, which is like a perfectly circular island. It's floating in the sky, in the clouds. And the people who live there kind of literally have their head in the clouds. They are obsessed with two highly related things, mathematics and music. And they think about mathematics so much that they kind of get distracted from life, to the extent that they have to take with them everywhere servants who carry with them a small bag of pebbles at all times, and periodically they hit their master in the face with the bag of pebbles to wake them up from their mathematical reveries so they don't fall off the edge of the island. Okay, so this is what Swift thinks mathematicians are always just sort of daydreaming. Okay, so he's got the Lilliputian mathematicians calculating Gulliver's size and volume because they need to know how much food to give him. So they say, well, it's a 12-to-1 proportion, and that means that Gulliver will need 1,728 times as much food as the Lilliputians, they say, because that's what his volume is. Now, a century ago, people would have known the number 1728 better than we know it now. It's the number of cubic inches in a cubic foot, it's 12 cubed. So the idea is, because Gulliver's volume, his mass is 12 cubed, 1728, times as much as the Lilliputians, he needs that much food. There's an issue with this. One issue is it's not true. That's the main issue. Now, Swift, we can forgive Swift for not necessarily knowing this, but actually, a bit later, a scientist, Kleiber, was wondering about actually what the metabolic rates of different animals were, in particular mammals. So he worked out, metabolic rate, how much energy you need in a day, so how much food you need to consume, how many calories. And if you're a mammal, so there's a couple of things going on that you need energy for. Obviously, all the cells in your body need energy, you need, organs need to be kept going, and you'd think the amount of energy they might need could be roughly proportional to, like, your volume, your mass. But mammals are warm-blooded, and a lot of the energy we use, particularly in a colder climate, is to keep ourselves warm, because we lose heat constantly from the surface of our bodies. Surface area is dependent on, that'll be like if you were scaling up and down, it ought to be the square of the scaling factor, right? Whereas your mass, if you're scaling, would be the cube. So we might think the metabolic rate will be somewhere, it won't be quite proportional to your mass, it might be a bit less because of this loss of heat from your surface. And so Kleiber sort of plotted on a graph, and you can see there's a reasonably good fit for what? For the metabolic rate being proportional not to the mass, but to a mass a bit less, to the power 3/4. So that seems to work pretty well for mammals, all of different sizes. So let's see what we get for Lilliputians. So their mass is like 1/12 cubed hours, right? 1/728 of hours. So if we plug that in, then they need that proportion of Gulliver's daily calorie needs. So a man typically needs 2,500 calories in a day, so a Lilliputian would need about, you can plug in the numbers, about 9.3. That's not very much. Life's good. Only there's a problem. The problem is, in Lilliput, it's not just the people that are small, it's everything. It's a doll's house world. The people are small, the trees are small, the animals are small, the plants are small. Everything is this 1/12 scale. And that's a problem because food, it's a tragic news, but the amount of calories in 10 grams of butter is 10 times the amount of calories in 1 gram of butter, right? The amount of calories in a particular given food depends on its mass. So here's the issue. Calories in food proportional to the mass of a particular foodstuff. So let's take, as a very simplistic thing, a standard apple, in Gulliver's England, is about 100 calories, right? So it'd be a boring diet, but Gulliver could get his calorie needs from 25 apples in a day. It wouldn't be a good diet for very long, but he could do it. What about a Lilliputian apple? So that's one of our apples, but it's 1/12 in every dimension, so the volume is this 1/12 cubed. So a Lilliputian apple, if you work that out, it's got a tiny amount of calories, 0.057. Okay, fine. So Gulliver can have 25 of his apples in a day and get his calorie needs, but the Lilliputians, they, if you work this out, if you do 9.3 divided by 0.057, right? 160. They need 160 of their tiny apples in order to get their calorie needs. And in general, they need to eat over 6.5 times as much of their tiny food every day as we need to of our food just to get their calorie needs. So they're going to be hungry all the time. They're going to have like 18 or 19 meals every single day. They are going to fixate the whole time on where they're going to get food from. The agrarian economy of Lilliput is not going to be in a good state. They're not going to have time to go to war with the king of Blefuscu over which end you should eat your eggs. on, they're just going to be cramming eggs into their faces all day long to try and get enough calories. So bad news for Lilliputians on that front. But you know, if they were to come and visit us in England, maybe they'll have a better time. One other risk factor for small people is water. So you probably shouldn't go out in the rain if you're very small, because raindrops, so you know, to us are nothing, but to a tiny little Ariete here, it'll feel like being pelted with apples all day long if you go out in the rain, so maybe don't do that. But a more serious risk, especially if you're super small, like the children in the film Honey, I Shrunk the Kids, that they really are exposed to some dangers here. This is not, I have to tell you, a realistic picture. Because this kid, he is shrunk to 1/200th of his normal size. The thing is, water, and I guess this is milk, liquids have surface tension. And that's an intrinsic property of the liquid. Scale doesn't affect it. There's a certain amount of surface tension. It means whenever you immerse anything in water, so like whenever you get in a bath or something, you come out covered in a thin film of water. It's about 0.5 millimeter thick, negligible to us. So if you work out the weight of that water, it'll be your surface area, the volume of it will be your surface area times 0.5 millimeters, right? And then you can work out the weight of that. It's about 900 grams, right? Which is not, you know, we can barely notice that. But if you're tiny, and we work out what happens there, suddenly that starts to become a lot more important and significant, because as you shrink down, your surface area is shrinking less fast than your volume. So as a proportion of your volume, that amount of water is suddenly more significant. So for a Lilliputian, it would be like when you get out of the bath suddenly feeling like you're carrying an extra 14 kilograms of weight, which you would notice, right? For these kids, they're 1/200th of our size, so I worked it out. They weigh 9.4 milligrams, but unfortunately the water that immediately engulfs them weighs 23 milligrams. So that is not a good situation. He would be completely engulfed in this, totally immersed in this, I guess, this milk, and not a good outcome. I don't rate his chances. So this is kind of dangerous. So there are, again, pros and cons of being small, but at least you can move around. Now, we've talked about creatures, about mainly big and small humans so far. What about big and small animals? Now, the thing is, we know that in nature, there are big and small animals, right? So how can this be? You know, have I just accidentally proved that elephants can't exist? No, because nature doesn't just scale things up or down, right? So this little duck picture was drawn by Galileo to illustrate this point. Bigger animals, because their volume is growing faster than the cross-sectional area of their bones have to get proportionately thicker in order to support the extra weight. So your elephant here will have much thicker bones and legs proportionately than the tiny little mouse scampering around. So that nature makes adaptations, evolution makes it possible to be lots of different sizes. But there are other challenges which you know, evolution has to cope with. One is about heat loss. So the smaller you are, if you're a mammal, the smaller you are, the bigger the impact of the heat loss from your surface area becomes compared to what heat you can produce. So smaller mammals are likely to be furry compared to the elephants, and they're likely to be sort of more of a spherical shape. That's the smallest surface area for a given size. And you know, they don't live in very cold places. So you can get Arctic foxes, but you can't get Arctic mice. But even in the Arctic, and even a single animal obviously has different stages of life, and the younger animals, they are proportionally losing a lot more heat compared to the heat they can produce. And so often the young of a species will have something like this adorable little seal pup, thick coating of fur, thick layer of fat, you know, puppy fat. That's there for a reason, to deal with that heat loss from being small. Okay, so potentially we can get big animals. They aren't going to be exactly like the smaller ones scaled up. So then what about the sort of animals that you see in stories? The kind of the giant spiders. And okay, this is an old movie poster, but Aragog, right in the Harry Potter books, giant spider. You've got Shelob in Lord of the Rings. Giant spider's definitely a thing that people worry about, right? Especially as I've said, it's yeah, we've already thrown one out of the window and now it's angry. So what about if it's also very large? Is there something we can do to stop this concern? Could you actually get a giant 100-foot spider, tarantula, evolving? It might be slightly different, legs might be thicker, but could you get this? Well, there are some pretty big spiders in nature, not as big as that. And notice the poor young lady again, clearly, as I've said. Yeah, I don't know what that's doing. This is a big spider, yeah, Goliath bird-eater spider. That's about the biggest spiders can get, it seems. But, maybe hidden away in the Brazilian rainforest somewhere. We never know, but, well, we do know. So I'm here to tell you as a mathematician, I can reassure you, you are not going to be terrorised by a giant spider. And here's how I know. Spiders are arachnids, and arachnids and insects do not carry oxygen around their body in the same way we do. So we breathe in, oxygen goes into our lungs, and then it gets transported around our bodies. That's not what happens for arachnids and insects. For them, they absorb oxygen through their exoskeletons, through their outside. And then it goes into their body through little tunnels called tracheae and gets transported around. So we're going to get a square cube law thing that's going to save us here, because let's say we took this spider and tried to make it, just scale it up by a factor of 10. So what's going to happen? The amount of oxygen it will need depends on its volume. That will scale up by a factor of 10. Cubed, 1,000, right? So it's going to need 1,000 times as much oxygen. But it absorbs oxygen through its surface. So the amount it can absorb will depend on its surface area. When you scale up by a factor of 10, areas scale with the square of the scaling factor. So it can only absorb and take in 100 times as much oxygen, but it needs 1,000 times as much. So it can't, that doesn't work, right? It's going to suffocate. So we cannot get giant spiders, you'll be pleased to hear. There's one other kind of animal, fantastical animal, that we haven't yet discussed, and that is another beloved trope of fiction, and that is the animal that's like a normal animal, but it can fly, like Pegasus here. We get flying humans, and we get flying all sorts of creatures that wouldn't normally fly, elephants, for example. Will you ever see an elephant fly? Well, it's unlikely, and here's why. There's something that governs whether an animal can fly, and it's called the wing loading. So you look at the wings, how big would a wing have to be to keep an animal in the air, and this wing loading is the mass divided by the area of the wing. And if that's too big, it can't fly. So sort of mass per unit area of wing, in order to stay in the air, there seems to be this sort of theoretical maximum of about 25 kilograms per metre squared. Above that, the animal can't fly, and this works for machines as well. So, if we just try and scale things up, if you take a bird that's, on the edge of this, and they're fine, but if you were to try and multiply them by 10, scale them by a factor of 10, you get the same sort of problems we did with pressure, right? The mass will be 1,000 times bigger, but the wing area will only be 100 times bigger, so it will broach that threshold. And that's, of course, why big birds are not just like little ones scaled up. Sparrows and eagles look very different. What about Pegasus, then? How could he exist? I mean, his wings they're going to need to be quite big, right? Not like we're seeing here. Because if you work out what the wing area would have to be to support a mass of a horse, horse is quite big, they weigh about 500 kilograms. If you plug that in, then work out what wing area is needed, then you find, what's the wingspan of Pegasus? Well, he's going to need a very big stable, because he needs 40-metre wingspan. So that's, how is he even going to, I don't, it seems a challenge. So, what we have to say here, though, is, I don't want this to spoil our enjoyment of stories, right? What this tells us is that if we encounter one of these creatures, that appears not to be possible, what that tells us is something else is going on that is outside of our understanding. So, if we see a creature like this, probably means magic is real. So let's all hope. I'm just going to give you, just in the last couple of minutes, before we have some questions, a few comments on actually these kinds of deductions or implications of the square cube law. I mean, it's really fun to explore, what the possibilities are of fictional creatures and how they might be able to exist and what their lives are like. But this stuff really is very important in the real world as well. So we talked about flying animals. You know, we make flying things as humans. And it's important to understand these rules if you want to make airplanes that do well. So I'll just show you like this. Here's a very small airplane and a large one. These are commercial aircrafts. On the left, I think it's a Boeing 727, and on the right, a very much bigger one, an Airbus A380. So they're shown like to scale with each other. If we just make that look a bit bigger, so it looks as if they're the same size, you can see their designs are very different. You can see that to make that larger aircraft, the Airbus A380, its wings, the area of its wings has to increase much more than just scaling up the small one. You can see they're much, much wider. And this is because of the square cube law. You need that wing area to keep pace with the increase in mass, which it wouldn't do if you just scaled in the same way. Buildings, another one. You can make a scale model of a house out of cardboard, but you can't make a house out of cardboard. And the reason is, again, the square cube law says those supporting structures, you know, the cross-sectional area must keep pace, and the strength of the material, at some point, you know, if you're using cardboard, it's going to have to be so thick you're not going to be able to do it. There won't be any inside of your house, so then you have to switch to a stronger material, like brick. And then if you're bigger than that, maybe steel, reinforced concrete. So you have to change the materials, and even then there's an upper limit. And at that point, then maybe you change the shape of the building, and let's just say the pyramid's a pyramid shape for a reason, right? Buildings really do have to pay attention to these things. You can't just scale them up without thinking carefully about the materials. And there's one final implication, and that's to do with scale models. Suppose you want to make a machine, and so to test it, you make a scale model. You have to be able to understand what this tells you about the full-size machine. You can't necessarily conclude everything will be the same. And a famous example of this, sort of in reverse, is in the early days of steam engines. On the left, there was this design for an engine that was used for taking water out of mines. It's called the Newcomen engine, so Newcomen designed it. It was raising power, raising water with a power made by fire, right? Exciting. Steam engine. And it worked, but it wasn't very efficient. So what happened was they would heat up the water inside, and then they would cool it down quickly, and so its volume would go down, and then that would create a partial vacuum, and so that's what would happen. Heating and cooling, heating and cooling, heating and cooling. It wasn't very efficient, but it did work. And Glasgow University had a model of this exciting machine, but it didn't work. So they got a local instrument maker to come and have a look, say, what's wrong with it? What have we done wrong? And they hadn't done anything wrong. They had replicated this machine exactly, but just at a smaller scale. And what the instrument maker realized was that the inefficiency at full scale, which was caused by like too much heat loss from the surface, and it's hard to then make it back again by heating, the surface area of the model was kind of proportionally much greater, and so it didn't work at all. So he said, okay, well, let's see, can we make one that actually does work? And to do this, he had the idea of creating a separate condenser, and this made the model work, but it also, when scaled up, made steam engines that were way, way, way more efficient. And this was like a really huge innovation that kind of kick-started the Industrial Revolution. And that instrument maker's name was James Watt. So that's his story, and kind of it all started because of the square cube law. So I will stop there and we'll have some time for questions. Thank you.
Thank you, Sarah, for that fascinating talk, and I'll certainly see giants and Lilliputians in a different light now. Does anyone have any questions?
He can go first. They can go first.
Okay.
So do any animals try to get around this, the way you mentioned, by having some sort of wrinkled or manifold skin?
Yeah, and
Surface area without
yeah, so there's definitely some of that, and also elephants, right? Elephants' ears are so big in part because that increases the surface area of their skin, and they can lose it because elephants, the problem is they get too hot. The tiny creatures, they're too cold, but these great big creatures. So having a bigger surface area, and also, yeah, they do have kind of wrinkled skin. Another kind of place for wrinkling, let's say, is actually inside us in our lungs. So to take in enough oxygen, our lungs have very intricate, wrinkly type surfaces in order to increase the surface area and therefore be able to take in more oxygen through that. So there's definitely adaptations that can do this. So yeah, if you to get bigger, we kind of had to, lungs themselves are an adaptation that allows us to be bigger. Yeah.
I was curious if with the Hagrid example, if the bone is growing,
Yeah.
does as the giant would grow, would the pressure coming down on it, would it strengthen the bone? Would it lead it to create more within the bone itself? Would its structure become stronger? So would it not kind of learn to become stronger?
So I think, yeah, if such a creature were evolving and growing in that sense, evolution doesn't just scale things up. So yes, to some extent, but if you look at examples of, there are a handful of people who perhaps have disorders due to like growth hormone not being produced at the right rate or not stopping being produced, and people who get very, very tall, then they do really struggle with having like bones that break and things, because you can adapt to some extent, but yeah, your bone density is there'll be some maximum beyond which it's not possible. And of course, yeah, astronauts go into space, I think they lose bone density, don't they? Because with the lack of gravity. So there are adaptations, but it wouldn't be enough to save the Brobdingnagians. I think that's fair to say. Back.
We start off very small and then get a lot bigger.
Yeah.
I'm just wondering about, is there anything you can say on the sort of how that would adapt our outlook as we grow? For example, I imagine the heart rate changes due to surface area, etc.
Yes, so a fetus in the womb has a heart rate about double its mother's to begin with. That slows down over time. When babies are born, they have a lot of subcutaneous fat. The babies are chubby for a reason. It's to keep them warm. So there are those kind of adaptations, and it's quite useful that little toddlers are going to be less affected by falling because they do it a lot. It's good because they're close to the ground. It's all good. But yeah, so as we grow, yeah, these things change, and of course, our bodies are changing as well. So we have different proportions of fat and muscle and things as we grow. So yeah, the bodies of animals do make these adaptations for sure. Yes.
Would the square cube rule be applicable to fractals? Because I know some of them have infinite perimeter.
That's a great question. Would the square cube law be applicable to fractals? So I would say, and there are quite a lot of fractal-like structures in nature. I'm thinking of some kind of corals and plants like that. We'd have to think about some of these fractal curves. They're kind of they're secretly one-dimensional, masquerading as two-dimensional, right? So if you double all the lengths, then maybe in that case, you have to think about what the fractal dimension is. Yeah. So if you've got I'm thinking of something like the Koch snowflake curve. You're familiar with that? So its fractal dimension is about 1.26. So then you would imagine when you change the dimensions, then if you were to if you, for example, take 4 of those together, then 1, 2, 3, 4 like that, you've actually made something 3 times as big, right? So you'd have to think about what's the fractal dimension of your fractal, and then think about the according relationship you're going to have. So if it's between a length and an area, then the scaling factor. If it's scaling factor of k, then your snowflake curve would scale by a factor of like k to the 1.26, essentially. Yeah. Yes?
Thank you so much for the talk, and I'm sorry if this gets a bit philosophical, but we spoke about a lot about humans, but in fictional terms,
Yeah.
and I was very interested about your opinion. Would you say that our physical size and our scale influences how we perceive kind of who we are as humans, because we sort of have a set scale, we don't grow that big or that small, and kind of how crucial is the scale at which we exist to who we are?
Yeah, I think that's a good question. So, how crucial is scale to our worldview, essentially? I mean, it is. It's hard to say exactly. You know, we of course the world around us looks a certain way, and you know sometimes my daughter asked me about this. Like we have cats at home. Do the cats understand that this house was not built for them? If you know what I mean? Like they experience the stairs as being these great big things. Do they realise that we aren't experiencing the world in that way? I think it's certainly, you know, our outlook and the fact that we're the size we are means we can do things like go in the sea, you know, we can climb trees, and we can see a certain way. So if we were the size of ants, you know, would we be able to look at the horizon and think, maybe the Earth is curved? You know, so these kinds of deductions, these scientific deductions that we are able to make, in part because we're the size we are, and I don't just mean the size of our brains, but like the size of our bodies too, they, I think, absolutely have an important relationship to how we are, how we exist in the world. But yes. Yeah.
Yes, so you've mentioned several stories that most of us know about people being reduced in size.
Yeah.
And I'm thinking about communication because the frequency of a sound when it's produced by something like a vocal cord or a string or something like that is logarithmically proportional to the length of that.
Well, it's actually inversely proportional.
Oh yeah.
So yeah. So if your vocal cord's halve in length.
So if you're 12 times smaller than a person, than a standard size person, you will probably speak like 2-3 octaves higher, which would be like your normal speaking voice would be higher than the highest note that most sopranos can sing.
Yeah, absolutely.
So that would probably make communication quite complicated.
Yes.
And if you're like 200 times smaller, like
no chance.
That, we cannot hear that at all.
Yeah.
So I wonder, is that do you know of any stories where that has been explored, like the communication barrier that would create?
So I think the only thing I can think of actually is the name of it. There's a film where people get very, very small. Is it called Epic? Ooh, can't remember. But yeah, I remember in that film they do realise that they won't be able to hear each other. It sort of just sounds like a buzzing fly, right? The Lilliputians, you would just about, I think, be able to hear them because every octave is doubling a frequency, right? So if their frequency is 12 times as high, that's sort of between 3 and 4 octaves higher, which, if you think about the notes on the piano, we can hear those highest notes on the piano. It'll be very quiet, that's another issue, because how we make the volume of, you know, our voice, its lungs and everything. So we probably could just about hear the Lilliputians, but we're not going to sit and have lovely chats with them because we're just doing this the whole time. But yeah, I'm not aware of books that have dealt with this challenge.
Horton Hears a Who.
Horton Hears a Who! Oh, of course! Yes. In Whoville, everything's fine. Okay, I think we may need to stop. Sorry, I'll pass over to Mila and she's got a couple of words to say.
Yeah, so thank you again, Sarah. We've got some copies of Sarah's book, which is up here out in the foyer, and Sarah's happy to sign copies if anyone would like to buy one. But thank you very much for coming to the I&I today, and I hope you enjoy the rest of the Cambridge Festival, and let's thank Sarah one more time.